Hello everyone, my name is Tanmay Sharma and I am a Prime Minister Research Fellow from Mechanical Engineering Department of IIT Patna. And in today's lecture, we'll be covering the carburetor, theory, problem solving, and concepts related to the carburetor. So, let us start. So, carburetor, first, we'll have to understand what is carburation. So, the carburation is the process of preparing in IC engine a combustible fuel air mixture outside the engine cylinder is called as the carburation. So this is a complicated process and is achieved in the induction system. So basically, through carburation, we are preparing a combustible fuel air mixture, which is then sent to the engine cylinder where it is burnt using this spark plug. Then carburetor is that device makes or which makes possible the carburation or where the fuel which comes out of the nozzle it becomes atomized and it mixes homogeneously with the air which is coming inside and then the fuel air mixture mixes well and goes into the cylinder. So the device which makes it possible for mixing the fuel with the air is called as the carburetor. So the most important part of the induction system is basically the carburetor, although it is nowadays obsolete because it has a few disadvantages which we'll learn towards the end. Then, to talk about the main parts of a simple carburetor, we have the float chamber. So basically, this is the float chamber, and we have the nozzle with the metering orifice. We have the nozzle with the metering orifice. Huh? Excuse me. Then we have the venturi. So this is the venturi out here. So you will see that the area of the cross section is reduced in comparison to out here. So as the air goes through the reduced area, the velocity will increase. So that is the purpose of the venturi. Then we have the throttle valve. So this is the throttle valve, and through the throttle valve, we actually control how much fuel air mixture we need to supply to the engine cylinder. So let us read these few key points. So the fuel level is slightly below the outlet of the jet when the carburetor is inoperative. So you will see that this is the level of the fuel out in the venturi and this is the level at the float. And the level in the float will be slightly lower. So in order to not have a particular pressure head which will actually pressurize the fuel through this nozzle. And if the system is not operative, then we do not need the oil to pour out into this venturi, right? That's why we do not need the extra head out here. We need the level to be lower than this, and there will be accordingly no this pressure head to force this fuel out when the system is inoperative. Then the nozzle has fine bore. Yeah, the nozzle has fine bore. That's why when the fuel that comes out of the fine bore, it is itself it is atomized, and due to that, it properly mixes with the air. So the air, since the surface area to the surface volume, the surface area to the volume of this very small fine droplets of fuel is very high. The surface area to the volume. So that way, it is very easy to evaporate the fuel by the incoming air. And generally, in order to facilitate the evaporating, sometimes this inlet manifold is heated up also. That also helps. But primarily, that's due to the bore at the nozzle, which makes it possible. When the oil issuing from the jet is in form of fine spray, yeah, we talked about it. Then it vaporizes quickly and mixes with the air. Yes. The air fuel mixture enters the engine cylinder, and that the amount of air fuel mixture which is entering the engine cylinder that is controlled by the position of the throttle valve. That also we have seen. So as the throttle valve is wide open, the area which is exposed to the pathway is high. Then more amount of fuel will be supplied to the engine cylinder. That way, the throttle valve is controlled, and we actually control the throttle valve with our either if we talk about the accelerator of the uh, engine, the this bikes, or if we talk about the this foot pedals, then that also is controlling basically the throttle valve. And when we uh, put some pressure onto the foot pedal or the accelerator in the bike, then what happens is the throttle valve opens, and it opens up, gives a higher area for the fuel air mixture to go inside the engine cylinder. Accordingly, a huge fuel air mixture, a large amount of fuel air mixture goes inside and solves the purpose for which it is done. So, mixture requirements from the carburetor. So the carburetor is there to provide air fuel mixture into the engine cylinder. So we need to understand what is basically the requirement of this mixture. So for that, we need to first understand what is the stoichiometric ratio. So for any um, amount of fuel that is present in with the air, the amount of air that is required to completely combust the total mixture is definite. So that is almost around 15 is to 1. So that is, this ratio is called as the stoichiometric ratio. It is the ideal or perfect ratio of air to fuel required for the complete combustion of fuel. So that is 15 is to 1. And why it is 15 is to 1? So that is actually if you solve the complete combustion, this mix this reaction, what happens during the complete combustion, then that reaction is given by this. So CXHY, so we have the fuel which is a organic compound, and we need to supply some amount of oxygen in X and Y, which depends upon the X and Y, and accordingly, if we have complete combustion, we will only have the CO2, carbon dioxide, and there will be no carbon monoxide, which we want, because carbon monoxide is so harmful. Oh. And in that way, if we need to calculate how much is the oxygen that we need to supply, that is X plus Y by 4, you will find that the fuel to air ratio will be minus 1. So that's how the stoichiometric ratio is known. And now in the engine cylinder also we need complete combustion, and but you will see that for different cases the complete combustion is not uh, desirable. So rather we will have to shift from the stoichiometric ratio, and why it is needed we will see to this now. So basically, if we have if we need to map the air fuel ratio with the load, means load indicating the net power that we need to generate out of the system, then mm, we will have a map like this. That is the air fuel ratio. Mind it that air fuel ratio is increasing in the downward direction. So basically, this is the fuel air ratio as well. If it is increasing in this ratio up, so air fuel ratio decreasing downwards, and the load which is increasing in this way, then you will find that when the load is quite less, meaning the system is not operative or it is operating at a very slow speed, then we actually need a very low amount of air fuel ratio or very high amount of fuel air ratio at during the ideal system. So you must be thinking that the load is less. Why do we need extra amount of fuel to burn if we are not having that load, right? So that's a very valid question, and we have an answer to that, and we will study later. So initially, at the ideal system, the load is very less, and accordingly, still we need very high amount of fuel air ratio or low amount of air fuel ratio. Okay, means the fuel content will be higher, and when the load is increasing, so there is a transfer from idle to the main metering system. So in the main metering system, it is the that system which supplies the fuel. That system of the carburetor arrangement or the inlet manifold arrangement which supplies the fuel to the engine cylinder when it is operating at a very economic load, or the load range out here. So that is the normal load system. So that is being the engine oil being uh, supplied by the main metering system. So there you will see that the air fuel ratio is slightly higher than the stoichiometric ratio, that is 15 is to 1. It is a little bit higher, and we need to supply more amount of air for a particular amount of fuel in comparison to the stoichiometric ratio. We will also understand why we need to do that. Then, when there is a large requirement of load, so the load is excess right now, and we want to operate the vehicle in this amount of load, then we need to supply a rich mixture of fuel. So the air fuel ratio will decrease, or the fuel air ratio will increase. So we need to supply high amount of fuel for a particular amount of air in comparison to the stoichiometric ratio. So this is the load and air fuel ratio map of what we need to achieve in a vehicle operation. And we will now see that each of the zones that you see, the three zones, the idle system, main metering system, and the power system, and the main metering system. So these are the basic load zones, and we will see that why this kind of arrangement is required in these zones. So first is idling or low speed or no load to 20% rated power. So this is no load when load is zero, or the system is just standing in its position, but we need barely to that amount of fuel which barely uh, keeps the engine running. Okay, so for that, um, a high fuel to air ratio is required, as you can see here. Air fuel ratio is quite low, or the fuel air ratio is quite high. Why it is so? So for idling or low speed, no load to 20% rated power, why do we need that? So if you see now in this engine cylinder arrangement with this whole carburetor placed out here in the inlet manifold, so you can see that yeah, when the engine is running, so you need some kind of a pressure difference in order to bring the inlet charge inside the cylinder, also to expel out the exhaust this gases out of the cylinder. So basically here you will have atmospheric pressures because it is linked with the atmosphere. Also in the exhaust valve at the outer end, it will be linked with the atmosphere, so it will have a atmospheric pressure. The pressure difference which is happening out here inside the cylinder, that is basically driving the liquid this fuel mixture in. So higher pressure at the suction will indicate higher amount of air fuel ratio coming inside. And a higher pressure inside also indicates that the unburnt the burned gases or utilized gases or combusted gases, so that will move out of the cylinder very easily if the pressure inside the cylinder is quite high. But while you're operating at a idling or low speed, the at the first uh, stroke itself, at the very first stroke, you will find that the pressure difference between the exhaust manifold and the cylinder is not high. Why? Because the pressure generated inside the cylinder is not high, and this is linked to the atmosphere. That is, it is fixed at the atmospheric pressure. So the pressure inside the cylinder is not high because the speed is not high, and it is not getting enough fuel air mixture to burn to that part. We do not need that amount of speed or torque to be generated, or the power to be generated. So the pressure is low, and when it happens is that the exhaust gas, due to the pressure difference, low pressure difference, the exhaust gas is not effectively removed by the pressure difference which is obtained out here, right? Yeah. So accordingly, what happens is that if the combustible gases are not properly removed, the And also you will have to mind that the pressure at the inlet manifold is also very less compared to this. So the not a huge amount of pressure difference is existing, which actually drives the airfoil mixture inside into the cylinder. And accordingly, you will find that during the suction stroke, as the piston draws in the air, the unremoved exhaust gas, because it was not removed properly, exhaust gas mixes with the inlet air. So the charge, which is the volume of air or airfoil mixture, which needs to be present inside that cylinder top, it is limited, right? But in that same volume, the amount of in fresh charge is less, and the amount of exhaust gases is high. And that way, what happens is that the charge is diluted. This process is called as dilution, and it happens during the idling or very low speed conditions. Accordingly, the power generated during the combustion stroke will be very less because it comprises a higher amount of unburnt gases which has no utility during the combustion, right? So that way, what is the solution to keep the engine running now? Is that we will have to supply a very rich mixture of fuel to air ratio in order to compensate that. So if the fuel quantity in the inlet air is quite high, what will happen is that although the exhaust gas is present and it is not completely removed, the fuel content is quite high, and that will actually burn up, and it will compensate for the loss in the pressure inside the cylinder. So that way, higher um, fuel to air ratio is required during the idling or low speed, and that is also being depicted out here. So low air fuel ratio during the idle system, or a low speed system out here, and that way some amount of fuel is although lost, but at least the engine is running in a favorable position. So this is the idle system which actually makes it possible. So idle system meaning there is some auxiliary mechanism to this carburetor, which actually makes the this whole thing possible. Okay, and that auxiliary system is called as the idle system, while as the in the main metering system there will be different auxiliary system. Every auxiliary system will work in parallel, and that is being taken care of, and the idle system will finally take care of that the engine is running at no load or very low load conditions in the compensation of higher fuel. So that is the case of idling on low speed or no load to 20% rated power conditions. Next, we concentrate on cruising or normal power, 25% to 75% of rated power. So that is this case, 25% to 75% around. So that is this case. So cruising on normal power. And during this cruising on normal power, our main intention is to have fuel economy. And we need to save the fuel, right? So the main metering system, it supplies the fuel air ratio a little less than the stoichiometric ratio, or the air fuel ratio is little higher than the stoichiometric ratio, that is 15 is to 1. You can see this. So the air fuel ratio should have been um, at the stoichiometric ratio, but the air is supplied in a little excess. Why so? Let us see. So basically, when we are cruising or at a normal power condition, the mixture charge which is coming from the carburetor, it basically is not homogeneously mixed, meaning the air is not homogeneously mixed with the fuel. So if there had been a homogeneous mixture of air fuel at from the carburetor, then it would be very easy to burn out the whole mixture. But that is not the case right now. So when there is non-homogeneous mixing of the fuel, the ignition process will actually leave out some amount of fuel unburned, and that is a loss in the fuel, and that we do not need. Instead, what we do is that we supply air in excess, so that it compensates for the non-homogeneity in the mixture, and finally, no fuel will left unburned, and there will be complete combustion of the entire system. So due to the non-homogeneous mixing, the complete combustion does not happen inside the cylinder, and some fuel remains unburnt and is wasted, and we do not want that. So some more air is supplied in order to ensure complete combustion and no wastage of fuel. So that is the case. So that is the case for the cruising or normal power, that is 25% to 75% rated power. So this is the system, and the main metering system is another auxiliary system that is attached to the carburetor, which takes care of this to supply the fuel air ratio a little less than the stoichiometric ratio, or the air fuel ratio around 16.5 to 1. So you see around here. Next, we will talk about maximum power conditions, that is 75% to 100% of rated power. So at the maximum power conditions will be in this particular zone out here, right? So we need a very huge amount of pressure or torque to be generated by the engine cylinder arrangement, and in that case obviously we will need high amount of fuel, but again too high amount of fuel is required. A rich mixture is required, not only to increase the power, but also for a different thing which we will now learn. So rich fuel mixture is supplied, and the power system and the main metering system supplying rich fuel oil ratio. So this is the system responsible for supplying the rich fuel air ratio around. So this is the air fuel ratio 13 is to 1 that we talk about. It is lesser than the stoichiometric ratio, that indicates high amount of fuel. So as you can see in this, then what happens is that more fuel more heat, produces a higher heat energy, which gives more work output, hence higher torque or speed is obtained. So that we already figured out, that at a higher load conditions we need more fuel in order to create a more amount of this work done. But again, if we need a higher load condition, we could have already opened the throttle valve to the maximum, and maximum volume of the same air fuel ratio in the stoichiometric condition would have been supplied out here. In that way, high amount of fuel would have been already present inside. So why not we do that, and instead we have to supply a richer mixture instead of in the stoichiometric ratio. So that's the question, and we will learn about it why a rich mixture is required instead of just having a higher amount of mixture in the stoichiometric ratio. So what happens is that higher fuel content is also supplied in the cylinder, which is responsible to cool down the flame. Now, what happens is the during very high this pressure operation, the engine cylinder and the intake and the exhaust manifolds, these become very highly heated up, and it may exceed its this working conditions, and during that what happens, it may be detrimental to the exhaust and the intake valve and also the cylinder. In order to cool down the flame, or in order to cool down the exhaust manifold and the intake manifold, what happens is that we supply excess of fuel, and this fuel is now not in mixture state, it is rather in liquid state, and this liquid state, when it comes in contact with this components, what it does is that it will increase its temperature due to specific heat, and this specific heat will actually will take away the heat from this exhaust manifold, intake manifold, as well as the cylinder, and it will cool down the entire system. So all of the fuel is not burnt due to insufficient air. Unburnt fuel absorbs the heat produced in the film flame as specific heat. Okay, and when it absorbs the heat produced and it is expelled out, you're basically expelling out the heat, excess heat energy, and saving your entire system. So higher power indicates higher mass flow rate, hence high heat transfer to the exhaust manifold. So higher chances of manifold overheating, and accordingly you will need some amount of fuel to go there and absorb the heat in order to prevent the manifold overheating. So the unburned fuel carries away the heat energy and cools down. Okay, we know that by now. Now, let us talk about the carburetor theory and get how to design a particular carburetor through our knowledge of fluid mechanics and heat and mass transfer. So, carburetor theory, the basic working principle of a carburetor that I have already talked about. So, during the suction stroke, what happens? The air is sucked through the carburetor by the pressure difference across it created in the piston when it moves. So if this is the cylinder, when the cylinder moves from the top dead center to the bottom dead center, a huge vacuum is created, and due to this vacuum, a lower pressure is generated. This lower pressure, in comparison to the atmospheric pressure, will create a pressure difference. Accordingly, the air will flow in. Okay, as the air will flow in, it will increases velocity as it flows through the venturi throat, because the cross-sectional area is now decreased in comparison to out here. Accordingly, what happens is that the air velocity increases and the pressure out here decreases. Due to the decrease in the pressure difference is created across the float and the discharge nozzle, which is required for passing in the fuel. So due to this pressure difference, the higher pressure out here, lower pressure out here, so the fuel now moves out of the nozzle as a very fine spray. At a very small droplets, it will come out. Ah. So the low pressure at the venturi throat enables the nozzle to discharge fuel. Then the nozzle contains small bores due to which the fuel leaves as fine spray and atomizes quickly. So our main intention is that as soon as the fuel comes out of the nozzle, it completely homogeneously mix with the um, air, incoming air, so that the homogeneous mixture can later be conveniently burnt inside the cylinder. So that's why we need very small bores in the nozzle, and these small bores actually helps in atomizing the fuel coming out. Then finally, fuel air mixture or charge moves into the cylinder during the suction stroke. So through here it will move into the cylinder, although there will be a throttle valve out here which will control the amount of mass flow rate coming inside the cylinder. So we will be designing a carburetor, and by designing we mean that we need to find the expression of airflow and fuel flow rates as a function of carburetor geometry. This is very important. We need to find the expression of airflow rate and the fuel flow rates, the amount of air flowing and the amount of fuel coming inside. Accordingly, we will get the fuel to air ratio, and we will need that as a function of this carburetor geometry, or the throat area, the amount of pressure difference. So as per that, we will design the carburetor. And the equations that we'll be requiring is very simple. The basic fluid mechanics and thermodynamics, which you have already read in our undergrad courses. And that will be, the first is the Bernoulli's principle. And through Bernoulli's principle, and the second is the steady flow energy equation. So why two types of equations? So first, if we need a very approximate analysis of the air which is coming in, and we assume that the air is not heated up, okay, during its way, then we can rely on this approximate analysis, and we will solve the for the air flow rate using the Bernoulli's principle. But if there is some amount of heat energy uh, obtained by the air flowing inside this uh, cylinder, we will actually we cannot rely on the Bernoulli's principle. We will actually have to solve it using steady flow energy equation, and which will give us the exact analysis of the air going inside. That is a little bit difficult, as you can see, the exact analysis. So that's why approximate analysis is used. But again, both the knowing both the derivations is very important, and none of the derivation for the airflow rate actually affects the fuel flow rate, because the fuel flow rate is completely obtained using the Bernoulli's principle, because the fuel is still in the liquid state. So that's why we will it is in the incompressible state, and for air that is not the case, it is in compressible state. So if the heat energy is given into the air, say it will expand, and that's why we need to find a steady flow energy equation, as accordingly if no heat is supplied to the air, or the air does not get heated up, we will simply follow the Bernoulli's principle. But none of this will affect the expression of fuel flow rate, and we will see that in the subsequent slides. So case one. So we'll be neglecting the compressibility of air, which is the approximate analysis, and accordingly uh, imagining as the incompressible fluid air. So we will solve the Bernoulli's equation. So we'll apply the Bernoulli's equation at section 1 1 and 2 2. So this is section 1 1, this is section 2 2, and we will solve it. So P1 by rho A, P1 pressure 1 by rho A, and C1 square, which is velocity of air at 1 by 2. So this is the kinetic head, this is the pressure head, and you will find in the Bernoulli's equation there is also uh, this difference of height present out here. So the height is now not seen in this particular equation. The reason being, this is a horizontal section, and the height of this in comparison to the atmospheric level is same as this. Okay, so that's why no height difference is required in this particular equation. Then we have P2 by P rho A. So P2 by rho A, the pressure will decrease obviously, and as the pressure will decrease, the C2 will increase. The velocity of air at the throat will increase. And you can see there that the rho A remains constant, because uh, it is assumed to be incompressible, or the density will not change. So rho is the density of air, P1, P2, and C1, C2 are given like this, and everything is in the SI unit. Next, ah, we will assume initial velocity of air to be 0, or C1 equals to 0 for our simplicity, because in comparison to the C2, the C1 is quite less. That's why we can assume that. And density of air rho is to assume to be constant, since air is assumed incompressible. So finally we will have, by solving this equation, C2, or the velocity of air at the throat, to be 2 into delta PA divided by rho A, and delta PA is P1 minus P2. So the pressure difference across this is actually driving the fluid or the air at a higher velocity across the venturi. So that's seen out here. Next, we calculate the mass of air per second at the venturi. That is ma is C2A2 rho A. That exactly we know that mass conservation. So we put the expression of C2 out here, And finally, A2 is the area of the venturi in meters square, and based on that, we get this expression of mass of air per second. So the actual mass flow rate is obtained by multiplying the coefficient of discharge of venturi area. So when we are using a venturi, there is some losses due to the curvature and the geometry, and these losses actually does not yield the complete expression as like this. So we'll have to multiply coefficient which is actually lesser than 1, maybe around 0.7 to 0.75 or zero point 0.9. So that way, what happens is that, yeah, we are using a venturi, so obviously the coefficient of discharge is quite high, around zero point 0.9. If it is an orifice, it is around 0.7, that is quite low. And we'll have to multiply that factor to this in order to get the exact mass of air per second, mass flow rate. So similarly, for the flow of fuel, now we will calculate the fuel flow rate, and we will finally calculate the fuel air mixture. So the fuel flow rate, we have P1 by rho F equals to P2 by rho F plus Cf square plus 2 plus Gz. So how it is coming? So you will see that here P1, basically this. So this is actually assumed to be atmospheric. So here the float, the top surface or the liquid surface of the float, it is also in atmospheric pressure. So accordingly, what happens is that this one can be shifted to out here also. So there will be no problem because both are atmospheric, right? And P1 by rho F. So the pressure out here, atmospheric pressure out here by rho F, because so P2 by rho F plus the velocity, because the velocity, since the area is very high, you will not know the total amount of fluid going downward because the velocity is quite small, because the area of cross section is very high, and that's why the C1 is 0. It is not taken out here. Cf, on the other hand, will have a particular value, a very higher value compared to the velocity of fluid out here. Then Gz is um, the height difference, and uh, uh, which also contributes to the pressure difference, and that is the amount of the distance between the heights of 1 and 2. So that is done. So these are the nomenclatures, and finally, if we solve this equation, we will get the value of Cf to be 2 into root over 2 into P1 minus P2 minus G z rho F divided by rho F. So P1 minus P2 we already know, that is delta PA. In the previous expression we have used that, and this term again comes up, Gz rho F, and we will see the significance of this term. So it may be noted that due to petrol surface being lower than the top of the jet by jet meters, the pressure difference becomes this instead of rho PA. Yeah, that we noticed. Then mass of fuel per second mf is simply, okay, here there should be Cf coming in. So Cf also, and we will simply put in the value of Cf out here, and there will be this particular formula where delta rho F is the cross sectional. So AF is the cross sectional area of the fuel jet per meter square. So air fuel ratio becomes Ma by Mf, that we know. Finally, A2 we just have to put in the expressions 2 rho A into delta PA divided by AF into root over 2 rho F within bracket delta PA minus GZ rho F. So A2, we just simplify the equations right now, and finally we apply the coefficient of discharge at the venturi. For so for the air there will be CDA, and for the fuel that will be CDF, discharge of fuel out here. So if we apply that, we will get this particular expression, and If Z equals to 0, then it is uh, then the fuel is at the same level as that of the nozzle. So Ma by Mf equals to CdA by Cdf into A2 by AF underscore rho A by rho F. So, so that's the expression of that. Next, that was the previous expression was for the approximate analysis, and now we will see that how to solve for the exact analysis. So by considering the compressibility of air. So when the compressibility of air is taken into account, the air flow will change, but the fuel flow will remain unchanged because fuel is still incompressible. So we can simply use the Bernoulli's equation for that. So for only the air part, if we use the steady flow energy equation SFEE at sections 1 and 2 here, then we will get H1 equals to C1 square by 2 plus Q equals H2 plus C2 square by 2 plus W, and so this accordingly we will find that there is a heat input to the air, and there is a certain amount of work. Let us see which these values mean. So the H1 and H2 are the enthalpies of the section 1 and 2 that we know. Then Q minus W equals to H2 minus H1 plus C2 square minus C1 square divided by 2. So if we assume that the system is adiabatic, that is, there's a very fine insulation around this whole carburetor channel, and for that there is no amount of Q, no amount of this heat being transferred from inside to outside or from outside to inside, then we can assume Q to be 0 and W. So there's no turbine out here for which we are driving in some work, right? So in that way, there's no work done, so W can be 0. And also the inlet air velocity is quite less in comparison to the velocity at the venturi throat. So we can directly assume it C1 to be 0 in comparison. Okay. Then we will have C2 equals to 2 H1 by H2 root over. So now we will use of this expression enthalpy equals to Cp into T, where Cp is the specific heat at constant pressure, and H2 equals to Cp into T2. So we will finally get C2 expression as this. So since the flow process between the atmosphere and the venturi throat is isentropic, so we will follow this equation T2 by T1 equals to P2 by P1 to the power gamma minus 1 by gamma, and if you substitute, we get C2 equals to root over 2 CPT1. So here we will substitute in place of T2 by T1 the pressure quantities. So P2 by P1 whole to the power gamma minus 1 by gamma. Now the mass flow rate can be calculated as this. So Ma equals to A1 C1 by V1. So here V1 is the specific volume and A2 C2 by V2. So this is equal because the amount of mass, it will remain the constant by mass conservation. So V1 V2 are specific volumes at 1 and 2, and we will use this equation this isentropic equation. So P1 V1 to the power gamma equals to P2 V2 to the power gamma, and by that we will get the values of V2 or the specific volume of V1 equals to V1 into P1 by P2 to the power 1 by gamma equals to RT1 by P1 into P1 by P2 to the power 1 by gamma. So we substitute the value of C2 and V2 in equation 1.11.8 in the previous slide we had. So that is basically the mass flow rate equation. So there, the theoretical mass flow rate Ma can be given by this big expression that you can see out here, right? So previously what happened is that we knew the value of C2 out here, and we simply now put in the values of mass flow rate A1, so A2, C2 and V2. So A2 and V2 we needed to find, and we found out the expression of V2, and we put it out here with the expression of A2. So A2 is, no, we do not need no expression for that because it's a geometric condition, and we will find out using that. And finally we have C2 out here. If we put it, and finally we put the values of Ma and Mf, that is mass flow rate of air and mass flow rate of fuel, we will get the air fuel ratio out here to be this quantity. Now we have seen how to derive the exact analysis out here. So this is the exact analysis, and you can see such a scary expression, and the approximate analysis, which is relatively very small expression and very less scary. And we need to find out the utility of these in our carburetor theory. So basically, there are certain notes to it. So the first note is, it may be observed that no fuel flow will take place when the pressure difference is lesser than G ZF, G Z rho F. So what happens is, so here you can see, so the pressure difference across this should be greater than the pressure difference across this due to the height Z. Okay. So if this is not higher, so this entity will be 0, and or less than 0, that is not possible. And accordingly, there will be no amount of fuel going outside. So this jet, if it is as small as possible, that is good for us. But again, we need a particular distance in order to see to this that no fuel will leak out when the system is not operating. So when rho is greater than this quantity, the fuel flow will start, and the mixture becomes progressively richer. Okay. Then the minimum air velocity at the throat cause the fuel flow will, with given value of Z, can be given as follows. So the minimum air velocity at the throat to cause the fuel flow. So that is C2 of the air. So that is, so you will just have to uh, differentiate it, differentiate the equation for getting the value of C2, and you will get, this is the condition out here, to get the minimum air velocity to cause the fuel flow. Okay. Then at higher air flows, when uh, rho A is greater than, much greater than G Z rho F, that is fraction G Z rho F greater than divided by delta PA becomes negligible, the air fuel ratio approaches this. So that simplifies the system. So if you're given at very high airflows what should be the mass flow rate, then you will follow this particular equation, and that simplifies your entire system. So that's for the carburetor theory, and next we will try to solve at least two problems in order to ease us with these expressions. Oh. Okay, before solving that, there are certain notes like what is the disadvantage of this carburetor theory. So certain drawbacks. So what happens is that a reduction in the density of air reduces the value of AF, that is the mixture becomes richer. Why? Because if you see reduction of density of air, so where is the density coming inside? So it will be a evaluation of these properties, right? So in that case, or here simply if we do the approximate analysis, the density of air out here is rho A. If the rho is less, the air to fuel ratio will be less, meaning fuel will be higher in comparison to a particular amount of air, and the mixture will become richer. So eventually the carburetor has to adapt for this, and if we have a system operating at a higher this uh, so where does it happen? So we will see that now. So first, the higher air flows when rho PA, delta PA, or the pressure difference between the throat and the outlet from where the air is sucked in is large. Then the C2 is large and the rho 2 becomes small. Yes. So the velocity of the air at the throat, if it is quite high, then this thing will happen. And if the system is flowing, if the vehicle is flowing at very high altitudes, the density of air is small. Again, that will be the case. So the carburetor actually has to this been designed for a particular system, so it cannot be operated in different pressure levels. So thus a simple carburetor, the air fuel mixture progressively richer with increasing air flows and increasing altitudes. This is a very big drawback, and we need to actually accommodate for that. The other drawback will include like it cannot supply rich mixture required during idling and low load operation. So this is a carbureted simple carburetor, and with the help of idling system, main metering system, or the power system, we can actually accommodate for these drawbacks. So that has been done, and the drawbacks such as it cannot supply the simple carburetor cannot supply rich mixture during idling or low load operation, that can be overcome. Now again, for a simple carburetor, it cannot supply rich mixture from starting from coal. Okay, so what happens is that when at very cold countries, generally the car will not start even at the first uh, go. So it needs some time. So eventually what happens when the spark plug is starting, or generally it is a habit to first heat up the system by a certain inner heater, and accordingly the whole intake manifold as well as the cylinder, it will become heated up, and um, after getting heated up, it will be convenient for setting the this uh, combustion. And if once the combustion is initiated and sustained, the engine will keep on running. So if cooled, generally in order to sustain this, a rich mixture is required, because a high amount of fuel means high amount of energy is being drawn out, and it will quickly heat up the entire system. But that is not being uh, that is a drawback for the simple carburetor, and for that some auxiliary systems are required, which we'll be discussing in the next session. So some auxiliary systems are required in order to supply that rich mixture. Then it cannot supply extra fuel needed during acceleration. Yes, for power metering system, that comes as an auxiliary to the simple carburetor system, that can actually supply the extra fuel needed, but a simple carburetor, it cannot supply the extra fuel needed. Now let us solve a few questions, and finally we'll end up this session. So the first question is, a four-stroke engine having diameter and length of stroke as 100 meter, and actually that should be 100 mm. So 100 mm and 120 mm respectively is running at 1800 rpm. Its carburetor eventually has a 28 mm throat. Okay, okay, the throat diameter is given. The assuming coefficient of airflow to be zero point 0.8, density of air 1.2 kg per meter cube, and volumetric efficiency of the engine as 75%. Determine the suction at the throat. The suction at the throat, we need to find the airflow. So, so let us now dig deep into this question, and let us take a moment to analyze it, so you can try to solve it right now itself. So I will pause for 1 minute, and you can have the answer ready by then. Okay then. So let us start solving this problem. So we are given the diameter of the engine cylinder is 100 mm, zero point 0.1 meter. L is 120 mm, 0.12 meter, and the speed of rotation is 1800 rpm. Throat diameter D2 is 28 mm of 0.028 meter. The coefficient of discharge is zero point 0.8. Um, Density of air is 1.2 kg per meter cube, and the volumetric efficiency is 75%. And so we'll have to find the suction at the throat, right? So we will find out how much is the air required. Okay. By the suction at the throat, actually we mean the pressure difference at the throat. So if we find the mass flow of what this air so that is going inside the cylinder or will be required inside the cylinder, we will find the corresponding um, suction that will be required at the carburetor, right? So first we will find the stroke volume, which is simply pi by 4 d square into L into 4, because it's the four cylinder, four stroke engine. Then actual volume per stroke is um, eta volume. There is a particular efficiency to the stroke volume, not of the entire stroke volume is being utilized in having all the air. So the volumetric efficiency actually gives the actual volume of the four cylinder which is utilizing this entire air, right? Which is lesser than the actual air. Then actual volume sucked per second. So for a four stroke engine, we will have to divide it by 2, because for every 2 cycles there will be one suction stroke. That's why we'll divide for every 800. So 800 rpm means for 1 minute there will be, in 1 minute there will be 1800 revolutions. For 1800 revolutions only, the suctions will come. The suction stroke, total number of suction strokes will be 900, because after uh, these 2 cycles the suction stroke comes by, right? That's why we'll have to divide it by 2 and then multiply it by 1 by 60 in order to convert it to seconds, and finally we will get the amount of airflow rate, meter cube per second. So the amount of airflow rate MA is 0.05094 kg per second, which is great. Now next, as the initial temperature and the pressure are not given, the problem is solved by approximate method, that is neglecting the compressibility rate. So this is a very important note. So in problems, when to use the exact analysis, when to use the approximate method. So when the inlet temperature and the pressure are not given, so you cannot solve it by the exact method. So if the pressure is not given, then you will actually have to consider the approximate method. So MA equals to CDA into A2. So root over 2 rho A into the delta PA. So delta PA is the suction at the throat which we require. And finally, if we solve it for the delta PA, we will finally find delta PA equals to 0.04457 bar, or mm, 4.4 millibar. So 44.57 millibar. So that is our answer. So the suction, so in order to have a mass flow rate of 0.05 kg per second, we need to have a suction pressure difference across the throat of about 44.57 millibar in order to sustain it for the cylinder arrangement as given out here, and also the geometry of the cylinders. So that's the first question. Let us move on to the next question. So this question came in the AMI paper as in 2000 for Durga University. So a spark ignition engine on test consumes 5 kg per hour of petrol when running on an air fuel ratio of 16 is to 1. The engine uses single jet carburetor having a fuel orifice area of 2 square millimeter and the tip of the jet is 5 mm above the level of petrol in the float chamber. Okay, that's good. When the engine is not running, calculate the depression in the venturi throat to maintain the required flow rate through the carburetor. Assume specific gravity of petrol as 0.75 and coefficient of discharge of the fuel orifice as 0.8. So, what area of venturi throat will be required to maintain the desired flow rate? Density of air is given as 1.2 kg per meter cube and coefficient of discharge for venturi throat is 0.8. We have to neglect the compressibility of air. So since we neglect the compressibility air, we will directly focus on the approximate method. So let us take one uh, 1 minute to understand this question, and you can start solving it if you have understood. So let us resume after 1 minute. Okay, then let us start solving the problem. So we are given that the mass flow rate of fuel is 5 by 3600 5 kg per hour, so that is amount of this kg per second, and the air fuel ratio is 16 is to 1. Fuel orifice area is 2 millimeter square, and the height of the orifice from the level at the float is 5 mm. The specific gravity of petrol is 0.75. The coefficient of discharge is 0.8. The density of air is 1.2 kg per meter cube, and the coefficient of discharge for air at the venturi is 0.8. So for both of the thing, 0.8 is the coefficient of discharge. Next, we'll have to find the depression in the venturi throat. Okay, the depression in the venturi throat is basically just like the suction at the venturi throat or the pressure difference between the inlet of the air into the carburetor and the venturi throat. So that is the depression. Now we will find out the depression as first we'll have to find out what is the mass flow rate of fuel. Then uh, can we find out the mass flow rate of air? So for that we are not given sufficient information. So we have to find out from the mass flow rate of fuel. So from here we get to know that everything is given except rho PA, right? So we'll solve for rho PA. So this is the expression for using the Bernoulli's theorem. We have derived that in the previous slides. Then if we solve for rho PA, we will find the depression to be around this value. So we will have to solve this particular value out here, and so that is the depression or the pressure difference delta PA between 1 and 2 point, and the throat area 80 we have to find next. So throat area or can be find from the air flow rate. So air flow rate mass of air is 16 is to 1. We'll use the stoichiometric ratio 16 is to 1 into play, and we'll multiply the amount of fuel by 16 and we'll get the air flow rate. So that is 0.022 kg per second. Next, uh, MA equals to CDA, the mass flow rate is equal to the product of coefficient of discharge of air into the throat diameter into the square root of 2 into rho A into depression. And we have already found the expression of depression from this out here, value of depression, and we will just simply put in the value. So the value of depression is 539.21 Pascal out here. And that is sufficient to uh, draw in the air and make the process of carburation possible. So from here we will simply calculate the value of area of the throat, which will come out to be 7.72 into 10 to the power minus 4 meter square. That is quite good. Then and to just verify, you can see that the area of the fuel orifice is 2 mm square, and here this is 7.72 mm square. So obviously the area of the throat should be higher in order to accommodate the fuel orifice. So in that way, your answer is seems to be correct. So that way you can verify that. So that is 7.72 centimeter square. Now the third problem is the data sheet is given for the third problem. So we are given the petrol consumed per hour, that is 7.2 kg. Then the specific gravity of fuel is given. Temperature of air is given. Air fuel ratio 1 is to 15 is given. Diameter of the choke tube is given, so 24 mm. Height of the top of the jet above the petrol level 4.2 mm, and the coefficient of discharge of air 0.8, coefficient of discharge of fuel that is given 0.7. Atmospheric pressure is 1.013 bar. We need to calculate the diameter of fuel jet of a simple carburetor. So let us take a minute to understand this question, and we can finally solve this question together. And this will be the last problem for this session. So we can do it hurriedly. Okay, so let us try to solve this problem. So first, diameter fuel jet df, will solve for this. Simply, we know that the density is related to by the ideal gas law as T1 divided by R T1. The initial temperature is initial pressure is given, temperature of air is given, so we can find the density of air. The density of air will be equal to 1.176 kg per meter cube. Next, we calculate the mass flow rate. of air. So the mass flow rate of air is given as the product of area of the throat into the coefficient of discharge at the venturi throat into the product square root of the product of 2 into density into the depression depression across the throat, delta PA. So that way, if we put in the values, so the airflow rate, it is already given. I think suppose here airflow rate 15 into 7.2, so divided by 36. So 7.2 is given as petrol consumed per hour, 7.2 kg per hour. 7.2 divided by 3600, that is kg per second. And we will multiply with 15, we will get the mass flow rate of air, because the air-fuel ratio is given as 1 is to 15. So accordingly, this expression comes into play, and we will have to solve it for only the delta PA or the venturi depression at the venturi or the suction at the venturi. So we will find that delta PA is equal to 2922 Pascal or Newton per meter square. So that is a very justifiable answer. So we do not need a very high, it should not be very high or low. So we will go ahead with the suction pressure. Now the fuel flow rate. The fuel flow rate is given as mf equals to product of area of the fuel jet into coefficient of discharge of for the fuel into the square root of the product of 2 into the density of fuel into the difference between the depression at the venturi and the g jet rho f, which actually is due to the height difference between the float fuel level and the venturi, this uh, that the nozzle at the venturi, and that is actually required in order to do not waste fuel when the system is not operated, and we actually need it. So this is a necessary evil, as we can speak, and in this formula we actually will be left out with only the area of the fuel, and also that if it is cylinder, we know that it is only dependent upon the diameter, as this expression now we can solve for directly the diameter of the fuel jet, and eventually we will find the diameter of fuel jet to be 1.32 millimeter. So you see the diameter of well is only 1.32 millimeter, and this that is quite justifiable, and you can uh, you will have to cross check whether it is the with the units, you will get the feeling that your answer is correct or not. So in today's lecture we have learned about the theory of carburation, the process which takes place at the carburetor. Then we have learned about the derivation of the mass flow rate, which a simple carburetor gives. We have studied the derivation and approximate method while we ignore the compressibility of air. Then we also derived the mass flow rate from the simple carburetor using the exact analysis, where we take into consideration of the mass flow rate of this compressibility of air. Then we find out the mass flow rates, and we see that how a simple carburetor is not sufficient to uh, meet the demands at the different load conditions or different operating conditions of the engine, and so for that we actually need some auxiliaries in addition to the simple carburetor, which actually makes it quite functional to meet the demands, regular demands. So one of the demands can be simply accelerating. We need a richer mixture fuel, right? The load is increased. At higher load, we need richer mixture fuel, that we have understood. And that cannot be supplied by the simple carburetor. Instead, we need some auxiliaries or the power system or at the idling system. We have learned in this session that higher this fuel air ratio is required, richer mixture is required. That cannot be supplied by the simple carburetor. We need a idle system, and in the simple metering system, it's in the simple running also at a normal load, we need excess air than the stoichiometric ratio. That we have learned in this session why. And in order to uh, provide that, the simple carburetor is not enough. We need a power main metering system. So we will learn about these auxiliaries in the next session. And after solving for this simple carburetors, knowing its drawbacks, we have also simply started solving a few problems, three problems to speak, in order to ease into the carburetor. And in the next session, we will solve a lot more problems in order to become very confident about the carburetor. So that's all for today's session. Thank you, and I hope to see everyone in my next session. Okay then, bye bye.